Great pleasure for me to introduce Francis Brown, who was originally an undergraduate at Cambridge, but has made his career in France. He's now at the University of Paris 7, and he's going to talk about multiple zeta values. I'm very glad to have him.
First of all, thank you very much for the invitation and for the introduction. So I'm going to talk about multiple zeta values. And let me begin with a bit of history. So let n1 to nr minus 1 be integers greater than or equal to 1, and nr an integer greater than or equal to 2, then the multiple zeta value zeta n1 up to nr is defined by the following nested sum: 0 less than k1 less than kr, 1 over k1 to the n1, kr to the nr. And this sum converges and defines a real number, which was first introduced by Euler in the 18th century. And there are two important quantities associated with this number. One is the weight, which is the sum of the indices to nr, and something called the depth, which is slightly more mysterious, and it's the number of indices r. So the first thing one notices when studying these numbers, k is the summation indices. K1 up to kr. Sorry, maybe my writing's not very clear. K1 up to kr. They're just summation indices. And the first thing one notices is that they satisfy very many relations. I guess historically one of the first, which is due to Euler, is that the even values of the Riemann zeta function, positive integers, are certain explicit multiples of powers of pi. So Euler computed the multiple exactly. Another fact which is due to Euler is the simple quadratic identity zeta m times zeta n equals zeta m n plus zeta n m plus zeta m plus n. Of course, I assume the indices are such that the sums converge in every case. Proof of this is very simple. You just write out the definition: 1 over k to the m times 1 over l to the n, and you decompose the domain of summation into three pieces: k less than l, k greater than l, and k equal to l. And each of these three pieces corresponds to one of these three terms here. So this identity is also due to Euler. I think that what happened was that, having proved that the even zeta values are related to pi, he was trying to see if there were polynomial relations between zeta 3 and pi. And the idea was, by messing around, by sort of linearizing the algebraic relations and messing around with these numbers, you'd eventually find some polynomial relation. And of course, he never found one, because we expect that not to be the case. So now let me set Z to be the Q vector space of multiple zeta values. And by generalizing this kind of formula, it's very easy to see that the product of any two multiple zeta values can again be written as the sum of multiple zeta values. And that proves that this is, in fact, an algebra. So let me then also write zeta subscript n for the vector space spanned by the multiple zeta values of weight n. So what you can do at this point, because these satisfy enormous numbers of relations, one can try to figure out what's going on. And I can write the following table. So in the weight 2, 3, 4, 5, 6, 7, 8. So there are two things you can do. One is to compute these multiple zeta values numerically to very high order and try to look for relations between them using some lattice reduction algorithm. Or you can try to write down all possible relations you can think of and solve them to try and guess a basis. So here I'm going to write down a putative basis for Zn in weight n. And it looks like this. So by Euler's theorem, zeta 4 is also zeta 2 squared up to rational. Here we have zeta 2 cubed. Here we have zeta 7, zeta 5, zeta 2, zeta 3, zeta 2 squared. And here something interesting happens. You get the first non-trivial multiple zeta value, zeta 3, 5. You get zeta 5 times zeta 3, let's say, zeta, zeta 2 squared, zeta 3, and zeta 2 to the 4. So this is sort of conjectural because we don't know that these numbers don't satisfy linear relations. That's completely an open problem. And if I write dn to be the dimension of this space, you find that you get this sequence of numbers, at least conjecturally. So this was first done by Donzagier, and he made in the 90s the following conjecture that the dimensions satisfy this recurrence relation, and furthermore that that Z is the direct sum of its weight homogeneous pieces. In other words, that there are no, well, Z0, of course, is just defined to be Q. So this says that there should be no relations between multiple zeta values of different weights. So the question then arises, then, can we write down a basis for these numbers? And in fact, the natural thing to do would be to look at something like zeta values which have totally odd arguments, and then some power of pi. So I can write this as zeta 2 to the k. And so this actually certainly fits the data up to 8, and there are very good motivic reasons for thinking that this should have been a base. But something goes horribly wrong. And so much more recently, Gangle, Kaneko, and Zagier exhibited this relation, 339 plus 150, zeta 57 plus 168, zeta 75, 1 zeta 12. And so this shows that this thing cannot be a basis. And in fact, these sort of exotic relations are in a correspondence with cusp forms for PSL2Z. So in other words, for every cusp form for the full modular group, you can explicitly construct some exotic identity between multiple zeta values. So that says that this basis is somehow pathological, and the structure is extremely complicated because it contains all this data coming from modular forms. So somehow this is bad. And sort of the way out of this is the following theorem. So my first theorem, and this was a conjecture due to Michael Hoffman in 97. And the answer, in fact, is very, well, I found it very surprising, is that every multiple zeta value of weight n is a Q-linear combination of the zeta values where the arguments are all equal to 2 or 3. And of course, it's homogeneous in the weight, so the sum of the arguments equals to n. So this was extremely surprising. It's a very strange basis. It's bizarre that the most natural basis turns out to be pathological, and the extremely sort of naive basis turns out to be the correct one. So the second theorem is also a kind of folklore conjecture, and it says that the periods of mixed Tate motives over the integers, I'll try and explain this a little later, are precisely the multiple zeta values, but in which you have to also invert 2i pi. So it was known for a long time that multiple zeta values are, in particular, periods of mixed Tate motives over Z. The theorem is to construct all the mixed Tate motives over Z and to check that these are the only periods. Okay. So you might think that the proof of theorem 1, certainly not the proof of theorem 2, but the proof of theorem 1 might use these relations to reduce multiple zeta values down to that basis. It's not at all how it goes, and in fact, nobody knows how to do that. The way it goes, very roughly speaking, is a kind of Galois theoretic argument. And sort of the goal is to try to understand multiple zeta values as a sort of extension of Q as a kind of Galois extension of transcendental numbers. So there's going to be a Galois group that for now I'll just write G transcendental. It won't be a finite group or pro-finite group. It'll be a pro-algebraic group. And the idea is this group is going to move these numbers around in some way. And of course, this is complete nonsense. Completely hopeless because we don't even know if it's not known that if zeta 5 is irrational. So this should be. So it makes no sense at all to try to define how zeta 5 is going to be moved by this group, because for all we know, it may be in the fixed field. So this is complete nonsense. But we can get around this, and the main idea that I want to explain is how to actually construct a kind of Galois theory. And the idea is to replace the actual number, which is just a real number, with something that I call the Motivic multiple zeta value, with an m in the superscript. And this thing will be a more sort of jazzed up version of this number. It will be some mathematical object, and it will carry the action of a group. So the idea is then to do some Galois theoretic arguments on these things, and then you can retrieve the number by what's called the period map. And at the end, so you prove something up here, and then you go down and take the period, and you deduce something about actual numbers. Okay, so when you say period, I should explain how multiple zeta values are periods. And I'm just going to give one example. And I'm going to give the example of zeta 2 and explain why it's a period. So classically, a period means something obtained by integrating a differential form over some cycle. Or, in other words, you want to pair de Rham cohomology with Betti homology. And so the starting point is, of course, an integral. And this is provided by Leibniz, who showed that you could take many different integral representations, but this is a good one. So to prove this, to calculate this integral is a sort of undergraduate exercise. You just expand this as a geometric series in T1 and integrate variable by variable, and you get zeta 2. You get the definition. So this needs to be interpreted as cohomology or homology on some space. And so the space in question is what's called M0n plus 3. So it's the moduli space of Riemann spheres with n plus 3 ordered mark points. And this can be very concretely written as just the n-fold product of the projective line minus 3 points minus all the diagonals. So of course, M04 is just P1 minus 3 points. So let me draw a picture of M05. So here we have 0, 1, and infinity, 0, 1, and infinity. And so let me write omega is dt1 over 1 minus t1, dt2 over t2. That's the form we want to integrate. So that's certainly a 2 form on M05. So this is M05. Then the domain of integration x is the set of points where, let me take the open interval, doesn't make any difference. So x is precisely this shaded domain here. And then you find very quickly that if you try to interpret this as cohomology and homology, you can do that, but you run into a problem. A seemingly innocuous problem, which is that the domain of integration meets the singularities of the differential form in 2 points at 0, 0, and 1, 1. And of course, the integral converges, so that doesn't pose any problem from the analytic point of view. But in algebraic geometry, this is a serious problem. So the solution is to do some blow-ups. So I let pi be the blow-up of M05 at the 3 points 0, 0, 1, 1, and infinity, infinity. So on the picture, what that does is replaces these points here with a copy of P1 in white, here another copy of P1 in white, and here a copy of P1 in red. So that's M05 bar, the compactification. And so now if we look at this picture, you see that M05 bar minus M05 now has, if you count them, there should be 10 divisors. So A will be the 5 white divisors, and B will be the red divisors. They each form 2 pentagons. And now we just want to pull the integral upstairs to this space. This seems very laborious, but it's necessary, unfortunately. So let omega tilde be the pullback of the form omega, which is defined on some open. But you check that it acquires no poles on the exceptional divisors, and its singularities are entirely contained in A, the red divisors. And the domain of integration lifts upstairs to form an open pentagon. And you can take it, so it looks like this. So after blowing up, the domain of integration looks like this, approximately. And so x2 bar is the closure for the usual topology. So this is a pentagon. And you check that its boundary is contained in B. And so after all this work, what you've achieved is that the pentagon no longer meets the singularities of the integrand. So this is the key point. That after all that work of blowing up has had the effect of moving the singularities of the differential form away from the domain of integration. Maybe I'll move up a bit. Okay, and so nothing's changed really. The integral zeta 2 after changing variables is still just the integral of omega tilde over this compact polytope, x2 bar. Let me call this equation 1. Okay, so now, so that means that we've interpreted, oh, not yet. So we've nearly interpreted the integral as a pairing between homology and cohomology. So to do this, let me define M2 to be, in fact, we need the relative cohomology of M05 bar minus the singularities A relative to the boundary of the domain of integration. And so you can show that this defines a mixed Tate motive over the integers. I'm not going to explain what this means. I'm just going to exhibit examples like this to give an intuition. One way to think about mixed Tate motives, or motives in general, is through their realizations. So you can think of this as a pair of vector spaces, which is all we need, really. A de Rham realization, which is just the de Rham relative cohomology. So this is a graded vector space over Q. And it's computed by, because everything is affine, by global regular differential forms over Q. So if you want, this is the mapping cone of a complex of differential forms. So it's something very concrete. It's a two-dimensional vector space in this case, and it certainly contains this differential, the class of this differential form. Then on the other hand, you have the Betti realization. Give Betti cohomology. I prefer to think of homology, so I'll dualize. So H2 Betti is usual Betti homology. So we take now the complex points of this, this thing. So it's a smooth manifold. You can think of it just as a topological space. And this is absolutely standard relative homology. And so this domain of integration, the new domain of integration X, this pentagon, has a boundary. So of course it's a relative homology class because its boundary is contained here. So after all this work, what does this formula mean? Formula 1, this integral means that zeta 2 is precisely the pairing, the integration pairing between these homology and cohomology classes. So zeta 2 is the pairing, let me write it in the bracket. Oops. X2 bar. And that just shows that this is a period of this motive M2. And so what's the rough idea behind these motivic multiple zetas? So the north approximation is to lift, instead of looking at the number zeta 2 in R, we're going to consider a triple of all this data. So it'll be the motive M2, and then a particular class, omega tilde, in the de Rham realization, which is some vector space, and a particular class in the dual Betti realization. Okay, so here we've got all the geometric information about the integral encoded in this algebraic data, and you can retrieve the number simply by pairing these two things together. So no information is lost. Okay, so that's zeta 2. Let me quickly explain how the general situation goes. So in general, you take a bunch of numbers equal to 0 or 1, and you can consider the following integral, iterated integral. So here there's a semicolon at the beginning and end, and lots of commas in between. And this is the integral now over an n-dimensional simple x of this differential form. So I always worry about the signs here. And so this integral converges if the first epsilon is equal to 1 and the last epsilon is equal to 0. But apart from that, you have complete freedom in choosing these indices here. You can consider these integrals. So it's an extremely special case of Chen's theory of iterated integrals, which holds for any manifold. So let me then, a key observation due to Kontsevich is that the multiple zeta value, again by a very simple argument of just expanding the integral and calculating, is up to some sign precisely this integral in the case where an r minus 1. So I hope I haven't got my indices backwards. I think that's correct. So here, when I write 1, this isn't 10 to the power something. This is a 1 followed by a sequence of n1 minus 1 zeros. 1 followed by a sequence of nr minus 1 zeros. So this is due to Kontsevich, this calculation. And so if I so as before, we can write this down as something geometric on a moduli space. Let xn bar be the compactification of this thing, of the domain of integration. Let me call this omega epsilon this differential form. Again, we lift the differential form to desingularize moduli space. And the upshot is that this number is a period of the generalization. So of a certain motive I'll call Mn, which is Hn of M0 n plus 3 bar minus A relative to, An relative to Bn minus Bn intersect An. And so it was proved by Goncharov and Manning that this thing actually defines a mixed Tate motive over Z, whatever that is. So Goncharov and Manning. So there's another way to see that multiple zeta values are periods using the Motivic fundamental group. I choose to do this a slightly different way. So first I should say here is that here An and Bn are certain boundary divisors. Certain boundary divisors. So this thing is universal. It contains as periods, in fact, all the multiple zeta values of weight n. But actually, it's much bigger than that. It contains a whole bunch of integrals which aren't at all of this form, and which are very interesting. And Goncharov and Manning conjectured that these other integrals should also be multiple zeta values. So I showed that in my thesis, and I say this because there are physicists in the audience. This fact in the moduli space, that the periods of the moduli space are multiple zeta values, is in fact enough to explain why multiple zeta values occur so abundantly in quantum field theory and particle physics calculations. So now let me say something about mixed Tate motives. Okay, so this is an enormously complicated theory that's due to a very large number of people. So I can't hope to do it justice here. But let me just say then that MT of Z is a certain Tannakian category. That means it's an abelian tensor, rigid, and so on category. Of mixed Tate motives over the integers. So the definition is enormously complicated and very indirect. So the point here is that we have a very abstract definition of some category, and all we know about it is its structure, which I'm going to explain right now. And the only thing you can do really is to construct examples of objects in this category. And using the known structure, hope, if you're lucky, that you span the whole category. So you have this abstract thing, and you guess elements inside it. And if you construct the whole thing, then you've finished. And that's exactly what I'm going to do. So it's known how to do this in very limited cases. So since this is an abelian category, it's simple objects. I can write down as simple objects. And in this case, they are denoted by Qn, indexed by an integer, and these are called the Tate motive. So essentially, this is the cohomology, or homology of projective space. And so these are the building blocks. What are the gluing? What's the glue between these building blocks? This is described by the X1 groups in this category. And this is isomorphic to Q if n is greater than or equal to 3 odd and 0 otherwise. So this seems quite innocuous. It's an incredibly deep result. It really hinges on the work of Borel, who calculated the ranks of the algebraic K-theory over Q. And so these dimensions here on the right-hand side are given by the fact that the K-theory of Q is one-dimensional in precisely for precisely these values of n. So I guess this connects maybe with the next lecture in some small way. So the other fact, so we have these X groups, and then the other fact is that the higher X's all vanish. Okay, so that's what we know about the structure of this category. There's a much simpler way to think about it, using the Tannakian formalism. So for this, we need the fiber functor. It's a canonical fiber functor, which to a mixed Tate motive associates its de Rham realization, and that turns out to be a vector space over Q, in fact, a graded vector space. But here we forget the grading for the fiber functor. And so using the Tannakian formalism, you see that the category of mixed Tate motives can easily be thought of just as the representations of a certain group. So the Tanaka group associated to this fiber functor, which is G de Rham. So G de Rham is some very large pro-algebraic group, but we know that it's in fact it splits as a semi-direct product of the multiplicative group, which comes from the fact that these Tate motives are graded, and another group U, which is pro-unipotent. So it's in sort of infinite upper triangular matrices or something like this. And the action of GM on its Lie algebra gives it a grading. And we know from the above that this is, so non-canonically, isomorphic to a free Lie algebra with exactly one generator, sigma 2i plus 1 in degrees minus 2i plus 1 for all I greater than or equal to 1. So this is the standard dictionary of Tannakian categories. The fact that this Lie algebra has one generator in each odd degree, that's precisely this statement about the X. So these generators come from K-theory. And the fact that it's free is precisely the statement that the X2s vanish. So at the end, we have something very concrete. We just have a free Lie algebra with one generator in every odd degree. And a mixed Tate motive will just be a representation of a graded representation of this thing. So after all this, we get something quite concrete. So now let me, for later, just look at what the functions on this group are and try to enumerate them. So let me call AMT the universal enveloping algebra of this Lie algebra dualized. So it's the graded functions on this Lie algebra. And that, by this description, is something very concrete. It's just the free associative, non-commutative algebra on generators f 2i plus 1 in degree 2i plus 1. And so we should think of these. So it's as a vector space, the basis of this thing is just the set of all words in letters, and set of all words in these letters. We should think of these f odds as corresponding to the single odd zeta values in some sense. So after this, it's very easy to compute the dimensions of this space. I guess that's maybe too low. I'll move over here. So what's the Poincaré series for the dimensions in weight n of the functions on the Motivic Galois group? So this is just an exercise. How many words are there of fixed weight in some family of letters? And it's, of course, 1 over 1 minus t cubed minus t to the 5 minus t to the 7. And if you work this out, what you find is that this is 1 minus t squared over 1 minus t squared minus t cubed. And so here at long last, you see this strange role played by 2 and 3 appearing as if out of nowhere from this free Lie algebra. Okay, so now let me explain how to define Motivic multiple zeta values. So I explained how multiple zeta values are periods of some objects in some category, and that in this category we know its structure, we know how big it is. So that gives us some kind of upper bound for the space of these objects. So what we had was an object, Mn, in this abstract category about which we know very little. And I explained that the zeta value, multiple zeta value, is just the integration pairing of some domain of integration with some differential form so this is viewed, this element is in the Betti vector space dual. So it's just a Q vector space which has some filtration. And this is in the Durham realization, which is again a finite dimensional graded Q vector space. And so now the key point of the whole thing is that because of this Tannakian formalism, the Durham realization of an object in this Tannakian category carries, by definition, an action of the Tanaka group. So it has a U-Durham action. So this is the whole point of the construction, that we now see that this pro-unipotent group acts on these differential forms and moves them about in some interesting way. So you take an element of this group and you take some differential form in this cohomology, and it just moves it to something else. Okay, so this is the Galois action that I mentioned at the beginning. And so what is the Motivic multiple zeta value? Well, instead of, so the period is just considering the naive sort of pairing between the homology class and the cohomology class. And the Motivic multiple zeta value will be considering the whole orbit under the group. That's the idea. So in fact, the Motivic multiple zeta value is the function from U Durham to R, which to an element in the group maps the pairing of differential, the homology class with the differential form after moving it by this group. So, so if I put G equals the identity here, of course I get back the original multiple zeta value. But you want to consider all its Galois conjugates. So the idea here is that, so what is a relation between Motivic multiple zeta values? Well, it's a relation between actual multiple zeta values and which remains true after Galois conjugation. So the relation is true after all possible translates by this group. Okay, so what is the upshot? So after all this, what we get is a certain space of Motivic multiple zeta values, which is graded by the weight. So this is the vector space spanned by, so maybe I'll just write it. Hn is the Q vector space of Motivic multiple zeta values. Of weight n. And you can show that this is an algebra. The multiplication rules that I wrote down at the beginning remain true in this Motivic setting. And what we have is a period map, H, back down to real numbers, and it maps this Motivic thing to the thing it came from, the multiple zeta value. So in other words, this is just a contraption to lift certain real numbers into some abstract algebra of objects. And so you can ask, so what? But the whole point of it is that what we've gained is the action of this group. And you can show that this algebra is closed under the action of this group. So we sort of reinstated the Galois action on these numbers. So it's closed under the action. So in an ideal world, we'd know all the transcendence conjectures of these numbers, and we could just define it on the level of numbers. So this is an elaborate artifice to get around the fact that almost nothing is known about the linear independence of these numbers. But of course, this setup works in a much more general context. Okay, so now, how much time have I got? 10 minutes, okay. Right, I need to hurry up. So now let me come to the main theorem. So I'll just give a brief idea of how the main theorem implies these conjectures. The main theorem states that the elements zeta m n1 up to nr for ni equals 2 or 3 are linearly independent. So let me then deduce the results I mentioned at the beginning from this theorem. So, so H is the sort of the algebra of Motivic multiple zeta values, and they're in particular periods of mixed-state motives. So now let me define, you can do the same thing but with periods of all mixed-state motives. So let me define MT plus to be the functions on the Motivic Galois group, and then we also have to throw in something corresponding to zeta 2. So this should be thought of as the algebra of abstract periods of all mixed-state motives. And what we have is, in fact, a non-canonical embedding of so multiple zeta values are in particular periods of some mixed-state motives, so they should be contained in the periods of all mixed-state motives. So that's what we have. And then I can also look at what I call H23, which is the sub-vector space of these Motivic multiple zeta values spanned by these elements here. So this is the subspace spanned by the Hoffman elements. So we have three spaces of the very special particular type of multiple zeta values, Motivic ones, all the Motivic multiple zeta values, and all abstract periods of all mixed-state motives over Z. And we want to prove that they're equal. So what does the theorem imply? The main theorem implies that these elements are linearly independent. So in particular, it says that the dimension HN23 is at least the number of ways of writing an integer as a sum of integers equal to 2 or 3. That's what it says. And then the structure, all this business about the structure of the category of mixed-state motives, calculation I did earlier, shows that in fact that the dimension, the generating function, the dimensions of this space is exactly 1 minus t squared over 1 minus t squared minus t cubed. And then because I threw in this zeta 2 generator, it's going to cancel the numerator. And of course, this generating function calculates precisely these integers. So what this proves, the upshot is that in fact all these three vector spaces are equal. And so let me take each of these equalities in turn. Let me call that equality 1 and this equality 2. So what does equality 1 mean? Well, it says that every Motivic multiple zeta value is a linear combination of Motivic Hoffman elements. So in fact, it says that these elements are a basis for H. And then if I just apply the period map, I get the corresponding statement for multiple zeta values. In other words, that every multiple zeta value is a linear combination of these Hoffman elements. So that proves Hoffman's conjecture, theorem 1. And equality 2 says, so here it says that this is the periods of all mixed-state motives. These are the periods of this very special mixed-state motives I've constructed by hand here. And they're the same. So it means that, in fact, we've constructed all mixed-state motives from the multiple zeta motives. So the slogan here, in a slightly different language, is that the Motivic fundamental group of the projective line minus 3 points with some tangential base points, I don't want to talk about that particularly, generates, in other words, we've explicitly generated the category of mixed-state motives over Z. So in fact, the argument shows that these motives I constructed here, Mn, span this category, but you can, in a slightly different context, you can prove this statement. It's very similar. And so this was known as the Deligne-Ihara conjecture, which I think started off in the late 80s. And originally it was a statement about Galois representations, but this is a slightly stronger result in the Motivic context, which implies the original conjecture. And again, by taking the period map, so all mixed-state the periods of all mixed-state motives are multiple zeta values. So we get the theorem I wrote at the beginning, theorem 2. So in the remaining 5, so yes, I was just thinking that. Could I have another 5 minutes or so? Okay. So I have to do justice to my collaborators. So I'll just say a couple of words about the proof of this statement here, the main theorem. So there are lots of steps. I'm just going to mention one or two of them. The first remark is that it's given by an induction over the number of threes. So goodness knows why, but that's what works. And in fact, the initial step in the induction needed an argument that's nothing to do with the main argument of the proof at all. A completely sort of elementary statement. And when I wrote the proof, I could do everything except for this one initial step of the induction. And I wanted to know if it was known or if it was trivial or if it was impossibly hard. So I asked Don Zagier, and after a couple of months, he gave me the answer. So this theorem is due to him, which was kind of commissioned for this theorem. And this is the initial step, sort of the north step in the induction. So you take a multiple zeta value in the Hoffman basis with A2s, a single 3, and a certain number of two B2s. And so I conjectured the shape of this formula. I could prove it using Motivic arguments. But what he did is actually compute all the coefficients on the nose. Times zeta 2r plus 1, zeta 2, 2, a plus b plus 1 minus r. So he guessed these coefficients and then proved this by actually a remarkably tricky analytic argument using the Fragment-Lindelof principle, constructing generating series. He proved this. So the key point here is these complicated coefficients here. And so I'll just say that the way this proof goes, you'd think that it might be something geometric, but it's actually very combinatorial and very arithmetic. And it uses some miraculous properties of these coefficients. Essentially, what you do is you look at this algebra H, you filter it by the number of threes, so you grade it, you get a bi-graded algebra. You have to show that the Motivic Galois group acts on this, which it does. It acts trivially on the associated graded pieces. So that means that the Galois group, you can then look at the two-step filtrations on this H23 thing. And the action of the Motivic Galois group will factorize through its abelianization, which is canonical. So that thing you can calculate using a formula I'll write down in a minute. And if you do everything right and arrange all the bases in exactly the right way, what you can construct is some differential operators on these Hoffman elements that reduces the number of threes and reduces the weight. And what you have to prove is that the set of all these differential operators acts injectively on this space. And so to do that, you have to compute some gigantic matrix and prove that it's invertible. And the entries in this matrix are very complicated linear combinations of these coefficients. So you have to prove that a matrix whose entries are linear combinations of these things is invertible. And the way you do this is that if you order everything in just the right way, and you look at it two-adically, so in other words, you multiply by a power of 2 in each column, a suitable power of 2, and then reduce modulo 2, it's this piece which dominates, and the matrix becomes upper triangular, and you show it's invertible. So it's kind of a very complicated argument. I can't really say more about it than that. But what I would like to show, if I have a minute, is how the Motivic Galois group actually moves these multiple zetas around, because it's kind of fun. So let me, instead of writing the Galois action itself, let me just give a flavor of the Galois coaction, which is just the dual. So there's a coaction of AMT on H. That's the same thing as saying that U Duram acts on H. And in fact, we don't know this action at all. We only have some very partial information about it. So it factors through a different map, which we can calculate. So I take a quotient by zeta 2, the ideal generated by zeta 2, And we have some sort of elementary coaction here. And this gives us partial information about the true Galois coaction. So let me write down a formula for this to see what it involves. And basically, so it'll be defined in terms not of these multiple zeta values, but these iterated integrals I wrote earlier. They too have Motivic versions. So how does the Galois group act on these numbers, these Motivic gadgets? Well, it's, just to give a flavor of the combinatorics, it's the sum over dissections of a certain polygon of the product of the segments in the dissection tensored with the vertices of the dissection. So rather than writing out a very complicated formula, let me just give a picture to see how this goes. You can code this iterated integral by putting points on a semicircle. And for every term in this coaction formula corresponds to some inscribed polygon. This one, for example. So one particular term in this formula would be, on the left-hand side, the product of each argument in each segment. E2, E3, E4, E4, E5, 1, tensored with the vertices. So IM, 0, E2, E4, 1. So you have to sum over all possible ways of dissecting this. And it's even worse than that, because these elements, I haven't actually defined them, they're not necessarily of the same shape. They don't have 0 and 1 at the beginning and end. So then to get those back into these elements, you have to do some shuffle product business. So in all, it's quite fiendish. But that's the way the Motivic Galois group acts on these numbers, and we have to live with it. I think that's all I'd like to say. Thank you very much.